Thank you for coming along and watching this video called Systems Beyond POSIX. I am Curtis Miller. I'm a student and staff member at UNSW Sydney, and I also work with the Trustworthy System Group inside of CSIRO's Data 61. Before I continue, I should mention that if you want to submit questions, we are asking that you place them in the discussion board on the virtual hub. You can ask this. You can continue asking questions here after the presentation, and I'll be checking on those questions throughout the summit. However, let's get on with the show. I'll just do another brief introduction of who I am. I'm Curtis Miller. I work as a research engineer with the Trustworthy Systems Group at CSIRO's Data 61. I'm also a student and staff member at UNSW Sydney. Most of what I spend my time doing is working directly on the seL4 kernel. I've been working recently on mechanisms for removing timing channels, as well as real-time scheduling in the kernel. But today I'm going to talk about building system software on seL4, because we need to be able to construct and manage systems on top of seL4. And in order to do that, we need some sort of consistent interface that all of the applications doing this can use to manage resources, communicate with each other, doing things like speaking to a file system, networking and communicating with computers over a network, managing memory for themselves and their child applications, for scheduling themselves, and just communicating between themselves, their child processes, and system services. And so the first obvious question, I think, is to ask how this has been done elsewhere. The most common the most common interface used is the Portable Operating Systems Interface, or POSIX. It's an application programming interface standard. It doesn't give any details on implementation, but it is based on the interface provided by Unix and its derivatives since the 70s. It is implemented for many operating systems, including Unix and its variants, System 5s, NX, BSD, AIX, SunOS, Solaris, as well as non-Unix operating systems such as Linux. And it provides mechanisms for dealing with many common operating system concerns, such as managing processes, communication between processes, dealing with files, file systems, and hard disks, and communication between processes on different hosts across a network. And it has some mechanism for managing all of these resources as well. And there are a large number of applications that already target this interface. So one might assume that this would be a good interface for us to implement on top of seL4. It means we can use all of the software that already targets this interface. It's well known along with C, and it's tried and tested. And because it's tried and tested, we know that there are a number of fundamental flaws in this interface. There's been many extensions to the interface since its original inception in 1988 that have provided alternatives within the interface itself that don't have some of the flaws of the original set of interfaces. However, there are also issues in the POSIX standard that are so fundamental that they can't be cleaned up with extensions. So throughout this talk, we're going to maybe discuss why we probably don't want to implement POSIX as our primary interface for application development on top of seL4. POSIX is a large collection of interfaces, but there's a small core subset which is most frequently used. Most of the examples you'll see in the wild come from this subset because it's the easiest section of the POSIX standard to understand and interact with. However, this subset of POSIX, the portion of the interface that most typical software targets, is unsuitable for the sort of systems we want to build on top of seL4. It has patterns that ensure that applications will perform poorly and have large overheads. It can be difficult to migrate from this small common subset to the more performant alternatives that have been introduced over time. And the way resources are managed in POSIX comes with insufficient access control. So typical POSIX software doesn't optimize well, and it can be difficult to secure. The primitives that POSIX is built on have traits that are detrimental to the development of system software. And hopefully by the end of this talk, I'll have convinced you that what we really need is a more suitable alternative to POSIX. And throughout this presentation, I'm going to point out a few large fundamental recurring features throughout the POSIX interface that make it particularly unsuitable. So the first is the way that I/O and IPC tends to be implemented via copying bytes between processes. So some probably very familiar interfaces we have here are read and write, but there's other variants, things like fwrite, send message, put message, message queue sends. There are various ways to read and write data between processes on a single host, between processes on different hosts, between processes and devices, and they mostly look roughly like read and write here. They operate on a file descriptor. You specify a region of bytes somewhere in your process's address space, and you say either I want these bytes to be copied out, to be written somewhere, or I want to read bytes from somewhere and to have those bytes copied into this buffer. But copying is a fairly expensive operation. In order to do this copy, I have to physically duplicate the data in memory, and this has to be done by the CPU. I have to spend CPU cycles reading the bytes from one area of memory and writing them out to another. And in doing this, I also have to bring both copies of that data into my CPU processor's cache. My cache footprint doubles because I now have two copies of this data that I'm actively working on. And generally, we want to minimize cache footprints as much as possible in all of our software. And if we're doing multiple copies on this data to pass them between multiple processes, this overhead is going to scale with the number of times we need to pass this between processes. And if we're doing something fairly common on POSIX, like constructing a pipeline, then for every process involved in that pipeline, I'm going to be copying this data again. There is more optimal alternatives in POSIX, such as using shared memory and semaphores. And the way this works is you open a shared memory object, it's identified by a name, we map it somewhere in memory, and then everyone who has mapped that same object into their address space is able to observe changes that everyone else is making to it. If we want to have any level of consistency in this shared memory, we also need some sort of synchronization primitive. In order to set this up between processes, we either have to have been copied from a common parent that already had that set up, or we need to somehow negotiate which memory object we're going to be using and which semaphores we're going to be using, which requires some existing communication protocol to discuss that over. And so we have to introduce some sort of bootstrapping process to set this more optimal communication channel up. The second recurring issue across the POSIX interface is that many of the interfaces are blocking, and this introduces a lot of overhead. Basically, all of the communication interfaces block by default. If I want to read data from another process or from a disk or from over the network, the thread that makes that read operation is going to stop executing until that result is available. This makes the easiest way to multitask on POSIX, well, at least now that we have POSIX threads, is to dedicate a thread for every task in the system that we want to execute. Constructing that thread, allocating it operating system resources in a stack whenever we start that task, and either destroying or reserving those resources for later reuse for subsequent tasks. And this means that when we have a task operating in a thread and it needs to request some input, then it's going to wait for that input to become available. And it's going to suspend all execution until that input becomes available. Another downside to using this threading model is that we're forced to deal with preemptive concurrency. This means that the concurrency issues we have to deal with involve considering the case that if we have multiple threads in the same process that are all operating on the same data, there is a very large number of interleavings, because at any instruction on any thread, we could be switching to another thread which could interfere with the first thread. It would be ideal if we could have, within a process, cooperative multitasking. And we can do this with non-blocking file descriptors or by using the AIO interface. And this works by modifying file descriptors to say that when we would block for a read or a write, or if we use the AIO read and write calls, then instead of suspending the current process and waiting for that waiting for that result to become available, instead we return immediately with values saying either the result's already here, or you'll need to poll again or submit this request again to see if it's completed. And there are also mechanisms for both the non-blocking file descriptor method and the AIO method that allow us to wait in bulk for many outstanding requests. However, these tend to scale poorly with the number of pending requests, because the way they work is that for signal or AIO suspend, we pass it an array of all of the requests that we want to block on in that call, and we wait only for those. And in cases such as a network server with tens of thousands, hundreds of thousands of clients, that means that that array needs to be very large, and the operating system, whenever we make one of these calls, has to be able to scan through that array to figure out what we actually want to block for, which makes it very expensive when we have a lot of things that we're waiting on. Another downside to this is that often these don't work with files in file systems. They'll work with pipes and network sockets, but if I want to read from a file, I'm usually still forced to wait, even in these situations. This is absurd to me because files probably have the worst latency of anything I could request data from. And the third thing and final thing I want to discuss that POSIX does all over the place, which is pretty detrimental to the construction of the systems we want to build, is its use of global namespaces. This is the default way that resources are shared in a POSIX system. I have some global namespace. I reserve a name for an object I want to insert into that namespace, and then if I want to pass that object to another process, I have to tell it what name I have given it in that global namespace. I can pass this as an argument on the command line, I could pass it via environment variables, or I could send it as some bytes, a string over IPC. And then that other process, if it wants to access that object, is just going to look up the name I've given it in this global namespace. So, what global namespaces do we have in POSIX? Well, there's the file system, which, when in doubt, most things are probably somewhere in the file system that we can look them up. With the real-time extension to POSIX, we have real-time semaphores and message queues. They have their own namespaces. With the XSI System 5 extensions to POSIX, we have different message queues and different semaphores, as well as shared memory segments. These are all things that have their own namespaces. The network also acts as its own global namespace. There is the assumption that an IP address and a socket address in one process is going to resolve to the same socket as it would in any other process on the system. Likewise, host names are their own namespace. There is the assumption that a host name resolved in one process is going to produce the same IP address, network address as a host name resolved in any other process on that same system. And there is a caveat. Also, processes and thread IDs are essentially a namespace of their own. There is one set of IDs that refers to all processes in the system. There is a caveat. Not all of these namespaces are unique. Some of them will overlap with the file system, and the consequences of that aren't exactly clear in the POSIX standard. And global namespaces introduce with them a number of problems. First of all, there is just the assumption that if I have access to a global namespace, I can see everything in that namespace. So I can see all of the resources, all of the files, all of the semaphores, all of the shared memory channels that everyone in the system has decided that anyone else needs access to. And in order to apply any security to that whatsoever, I now need to set access control parameters to every object, which is unnecessarily fine-grained. Generally, I will have groups of objects somewhere in my system that I want to apply the same access to, and I don't want to have to individually specify that for every object in that group. It would be nice. I'd preferably just like to apply it to that group of objects and then pass that group of objects around. There's also the fact that the the access control policy is controlled by the namespace. If the namespace doesn't support some specific way of providing access control, I can't do that level of access control. And because this is POSIX, what access control we have is fairly limited. For anything that lives in the file system, we can set an owner and a group, and we can set whether or not that owner can read, write, or execute that object, whether it's a file or anything else. We can set whether or not any process run by a user that belongs to that group can read, write, or access it, and then we can say whether or not anyone who is neither a user or in the group owning group can read, write, or access. And for many cases, this level of control is far too limited. So we have something that is far too fine-grained and not expressive enough to give us the sort of control over resources we need. And then not even all namespaces have a mechanism for access control. Some of those namespaces are just open to anyone who can enumerate them. Add into this that because everyone has access to a global namespace, anyone can just create objects in the global namespace that anyone else can read, introducing covert channels. If I'm trying to isolate two processes in a system, I don't want them to have any way of communicating with each other. But if the assumption is there that they both have access to a global file system that they can write to somewhere, then they can now start communicating with each other. And so it's very difficult to configure these global namespaces such that they have the level of access for all of the processes in the system that we want in a way that is consistent and correct. It's very easy to get this wrong. So, how do we provide a better operating system interface for seL4? Well, we need to make sure that we have some optimal interfaces. These are interfaces that are fast, that have very little overhead, and that are easy to create in a secure manner. These also need to be the default choice for all of our interfaces. The thing that you reach for first, that is going to be your first choice whenever implementing a system, needs to be the thing that is this fast, lightweight, easy to secure interface. It needs to be easy. In order to do this, it needs to be the easiest thing to use that is available. This doesn't mean removing everything and just presenting a difficult interface. We need to make sure it's easy to understand and ergonomic to use. We also need to reduce footguns. Anything that's going to lead you on a path that's going to give you a poor performing or insecure system needs to be gone, or at least very obviously unappealing. And the way we do this is to minimize copy-based communication. If copying is a problem, then we reduce it. We need to make sure that the default way to transfer data and communicate between processes is via shared memory. This means we need to make it easy to construct and propagate shared memory channels. So it should be easy to, between two processes, set up a region of shared memory and all of the semaphores necessary to synchronize access to it without much effort. And also to propagate this between processes in cases where there is a long chain of data being shared between processes. Synchronization primitives need to be easy to use in conjunction with this shared memory. And we should also minimize the mapping overheads by reusing existing mappings as much as possible. If blocking interfaces are a problem, we need to add asynchronicity to our interfaces. So it would be nice if there was only one fundamental blocking interface. There is one interface you can call that will block your thread. Every other interface is not going to block your thread. If you make a call to anything other than this one magic interface, then it's going to do as much work as it possibly can synchronously on the current core, and any point it's going to have to wait for some work to be done by an external core or by an external device. It's going to return to you immediately and say, I'll let you know when the rest is available. And then we have this one blocking interface that says, well, when the current process or the current thread has no work available to it that it could continue doing whilst waiting for inputs, that's when it chooses to block, and it will wake up as soon as there's more inputs for it to process. And we need to make sure this can be done in a way that can scale to tens of, even hundreds of thousands of requests with minimal overheads. Modern network servers have to and can deal with this many requests within a single process. And once we have this interface, we can compose our multitasking API, our multitasking mechanisms on top of this. If, for example, we want to operate in a way that doesn't have to deal with any of the complexities of asynchronous interfaces, we can use this interface as though it was synchronous by just pairing every request that could potentially return need to block with an immediate blocking operation that waits for that one input, and we never have more than one input being queued waiting. We could also provide user-level libraries for multitasking, user-level threading libraries, and what's becoming very common in many popular programming languages is to have a language-level construct that translates asynchronous interfaces to multitasking within the programming language. So you can write code that feels like you're writing synchronous tasks, and the language runtime provides a mechanism of interleaving those on a single thread in a way that is far more lightweight than you can do with threads, because the programming language knows how it can do this without having to allocate more than one stack. It knows how to do this whilst only preserving the minimal amount of state for each individual task. This can be a lot more efficient than what we can do with threads. And the only reason we would need to introduce threads in this world is to allow our process to execute across multiple cores. There should be no need to have any sort of end-to-end multitasking where we have one task per thread. And finally, for resource management, if global namespaces are the thing that's causing us problems, we get rid of global namespaces. We share everything via IPC. If you want to access a resource, then the way you access a resource is to talk to some service, query that service, and have that service send you the resource via IPC. And this means that if the service needs to apply any sort of access control policy, it can do that to any degree it likes. There is complete flexibility with how any service controlling a resource implements access control policies of those resources. We are not restricted to whatever the global namespace happens to support. This also means that we can apply ACLs on whatever scale we want. If we don't want to apply them on every individual file in the file system, but we just want to apply it to a directory tree and apply the same access to everything within that tree, we can apply it at that level easily. We don't have to worry about having accidentally set some file deep in the tree to be able to be world writable for some reason. And once we have this, we just remove global namespaces entirely. We don't have any sort of single global file system. We don't assume global network interfaces. And this means we have flexible ACLs, and we have far less pain in implementing access control to our resources. If we have this system, it then seems that we could maybe implement POSIX on top, and we could do that. However, if we were to then take POSIX and implement on top of these nice interfaces we now have, we'd reintroduce all of the issues that we were trying to avoid that POSIX had in the first place. So the only real reason we might want to do this is to support existing POSIX applications so that they can still work with the interfaces they've targeted, but they're isolated from all of the other processes in our system. There's no reason we would aim to encourage the use of POSIX or make it the primary interface for developing applications in our operating system. And probably the most reasonable way of implementing this is to just have a POSIX service, which provides the same interfaces that a POSIX application might expect, like all of those global namespaces and global resource management. And we'd probably have a POSIX service one for each application group we have, similar to having a container in Linux, except hopefully not nearly as painful to configure. So what is the operating system interface? How are we going to interact with the operating system on top of this? Because all that we've defined so far is what our primitives need to look like to construct this higher level interface. So the next thing we need to decide on is how we manage resources and access control in a standardized way. It's great if anything can apply its own access control and resource management policies, but if there's no standard way of doing this, it's going to be very hard to interact with and use. We also need to have standard interfaces for our common concerns, things like standard interfaces for files and file systems, networking and sockets, human interface devices, so on and so forth. And for the purposes of administrability and debugging, we should also be able to fully introspect everything in the system in a standardized way. The easiest way to do this is to have some all-knowing root component that knows of all of the allocations that a sufficiently privileged process can communicate with to introspect and like kill process groups and view the state of the system. But this is all stuff this is all an area for future experimentation and discovery. I don't claim to have all the answers at this point, but once we have a solid foundation, this is the areas we should probably be looking at next. So that basically summarizes how I think we should be moving forward on constructing systems on top of seL4 and what our operating system interfaces should look like. If you have any questions about this talk, I shall direct you to the virtual hub where I'll be looking at and responding to questions throughout the summit. If you're curious about any details that have come up in this talk, I can also direct you to A Fork in the Road, which is a paper that was delivered at HotOS 2019, which describes some of the issues with fork in particular, and also What Unix Cost Us, the Benno Rice presentation at LinuxConf AU from January this year, which goes into detail in some specific POSIX APIs and what pain they have brought us in the world. But beyond that, thank you all for watching. I hope you enjoy the remainder of the summit, and I look forward to seeing your questions in the hub.